I will be talking about program synthesis. And so first, I just want to say that I'm Jonàš, but this is also work with all of the amazing people you see on the screen. And yeah, in the top right is my best visualization of Rust synthesis. So let's start with some beginner example. So here we have some code that I took from Stack Overflow. I've very slightly simplified it. But essentially what the user is trying to do, they have some option inside their struct, and they're trying to convert it into a result. And you know, since I expect most people know Rust here, we can see what the mistake is. Well, they're just trying to move out the data from their option to get an owned T and then reborrow it only later on. And so, of course, the compiler complains at this. And then the user went to Stack Overflow to ask how can they fix that code? What can they do about it? Well, what if instead they could just go to a program synthesis tool and just give the tool a signature? So we just write the signature since we already have that, but we want to implement the function. So we just leave it as to do and give this to a synthesis tool. Well, the synthesis tool we're talking about today, that will just return error because well, that's the easy solution, right? So not only does the user here need to provide just the function signature like this, they can also add some specification to the function. So here they write that when we get in some an option with sum, then the result should also be returned as okay. And so now this forces the synthesizer to kind of return the actual correct solution that we want. And so when we send this off, then we do indeed actually get the correct solution where it reborrows straight away. And so the compiler is happy with this. And so what we've seen here, well, this is essentially what we're doing with deductive synthesis. So we'll get in some type signature from Rust, so some input types and some output type, and then also maybe some functional specification, which tells us that the requires tells us what shape the inputs can have, and the ensures tells us what the function should kind of do, what output it should return. And we give this to the tool, and it will work for a bit, and then at some point return some implementation for this function. And potentially it can also, if it's a recursive function, it might need some auxiliary helper functions, so it can synthesize those too. And here the key aspect is that it's in safe Rust. So there are already tools which do this approach for C, and we could just kind of try and translate the Rust signature to C and give the signature then to one of these C tools, and then put unsafe wrappers around the result. But that's not very pretty. It's not going to give you idiomatic Rust. So the kind of challenge is to come up with some way to actually abide by the Rust typing rules and the Rust borrow checker rules. And well, what we want is that if we then give this to a compiler or a verifier, such as Prusty here, that the result, it will both compile and it will verify out like straight away, where there's no kind of back and forth. By construction, the synthesizer will actually give you some solution which will be correct. And the reason for this, so why is it called deductive synthesis? Well, what the synthesizer is actually doing is it's looking for kind of a correctness proof. And so it has some functional spec, it has a type signature, and then it, in some logic, it kind of does some search, and then when it finds a solution, this solution corresponds to some Rust program. And since we've already found some proof, then we know that the program will be correct, both in terms of Rust, in terms of the Rust compiler, but also verification tools. And so now let's take a look at some ways we can use this tool. So as we already saw, we could use it for helping out beginners, where if they just are struggling with the Rust type system, they can't get the borrow checker to work, then they can use some synthesis tool to help them find the correct solution. But I mean, it's not only useful for beginners. One thing we can use it for is to fix issues in existing programs. So this kind of is also for beginners, but for everyone, where say the Rust compiler right now, it would return, if it doesn't say the program isn't correct, it returns some error. Well, you could use a synthesis tool to kind of actually even suggest a solution. So the Rust compiler already does this for very simple examples where you don't do the reborrowing correctly. But for more complicated examples, you could use a synthesis tool to actually come up with the full implementation. Additionally, what you can use it for is kind of migrating some data representation. So generally, the functions that do this, they're not very like heavy on the specification. So you can write a pretty lightweight specification, and then you actually get a good trade-off. So for example, say you have some data inside of a tree and you want to flatten it to a list or somehow rearrange some data without changing the data itself. And lastly, well, maybe something that's kind of hits for this audience. So imagine you're working with some complex API, say in the Rust compiler or something, and then you need to call some sequence of functions or something like this to get from one data type to another. You know you want one data type, but you're working with some global map or something. And so instead of kind of doing the simple auto-completion that you get right now, where it just suggests all of the functions that you have defined for some data type, you could kind of use a synthesis tool to chain these together and get a more complicated solution. And for deductive synthesis, the key kind of founding principle for all of these applications is that we're guaranteed to get programs which will be correct by construction. So now that I've kind of gone over it, let's hopefully take a look at a demo that, well, hopefully it doesn't crash or anything, nothing goes wrong. So here I've kind of prepared it that you can also follow along if you want. So you can type in this short link, and that will take you to this full link. I will be running the demo locally because in case the traffic kind of slows it down or something. But if you follow this link, then what it will take you to is here, this kind of playground that I've forked.
Okay. Jonas, can you please post the link in the chat, please?
Yes,
a lot easier.
I was planning to do that, but then what type of, yeah, you have that too. No, but actually that one, you should use this link. So it's like the shared code, so you should use this link, which will take the code from the gist. Otherwise, if you use the direct link, then you don't get the demo code. And so here in the playground, you might want to switch it to nightly, because that way then you can run the code as well. And what I've added to the fork here is this RusSOL button, which runs the tool and it will synthesize some function. So here you can annotate functions with synth, which just tells the tool you should synthesize this specific function and not all of them. And you can see here, if I run the tool, it should now give you back the implementation. And when it succeeds, it won't actually, it will just disappear and it will just replace in the implementation. So you guys can follow along while I do the demo here locally. So here in the demo that I've set up, it's we're working with a linked list. So we have a linked list definition where it's an enum. It can either be an empty linked list or a cons node. In the cons node, we get some payload, we get an element, a generic element, so we can instantiate this to be arbitrary. And then we also have a next pointer, so a next pointer, which is a box pointing to the next node. We could also kind of, there are various ways to represent this linked list, but here I've just picked the one that's easiest for the demo. But if you wanted to rearrange stuff, use an option, or instead of this enum, then it would also work. But okay, so the first function that we want to synthesize here is a singleton function, where it takes some generic element t, and we want to create a new linked list. And of course, since we're getting the t, we want this linked list to be a singleton linked list with just one element. So you can see if I run the tool on this function, we will get back some implementation. And what the implementation is, well, it's creating what we expect the singleton linked list. And one thing we can notice here is that actually, due to the Rust type system and due to the generics, we're getting this element t. We can't clone it. It's not, it doesn't implement, or it doesn't have the trait bound copy or clone or whatever. We can't do anything. So we only get one t. And so there's only two solutions to this function that we can actually come up with. One is just returning an empty list immediately, and the other one is returning the singleton. We can't return a list with two elements since we can't create two t's. And the tool here, it's being a bit smart. It's seeing that we're getting in some element t, and if we were to return an empty list, well, we'd have to drop this element t. Since we're not using it, it would get dropped at the end of the function. And so it tries to avoid that. So what we get is actually the expected implementation that we wanted. But this doesn't happen so often. Generally, you will need to write some specification above the function. So here we just have the signature and we got what we wanted. But generally, we'll need to write some specification. And for example, the next function we'll take a look at is a peak function, where we get an immutable reference to the linked list, and we want to get a reference to the first element of the linked list. So just the t itself. And well, we need some way to talk about linked lists. And here we do it in a very similar way to how many verifiers do things. Well, we write some pure function. And so this pure function, it's calculating the length of the linked list. And well, you can both execute the function, you could run it and actually get the result, but the tool also understands it in a mathematical sense, in that now it knows what a length of a linked list means. And therefore, we can write requires and say, well, this peak function, it's not going to work if we have an empty list because we have no t reference that we can return. So we require that the length is at least one or more. And so with this requires, we can run the tool and actually get an implementation as well. Again, the implementation here is not super complicated. We just want to show off the specification. And it's actually able to figure out that in the nil case, well, we can't reach it because of the requires, so it can just panic there. Whereas in the cons case, it returns the element that we expect. And you can see also if I comment out the requires, then it won't be able to find a solution because it's a bit of an output, but it says that it fails because it can't solve it for the nil case here. Moving on, well, let's take a look at how we work with mutable references. So here we have a push function where we're getting a mutable reference to the linked list and we want to add this new element. And specifying mutable references, well, for mutable references, we care both about the value of the reference before the function and after the function call. And to differentiate between that, we borrow the syntax from RusSOL. And so here with the star, we're dereferencing the self before the function call, whereas here with the hat, we're referencing after the function call. So what this specification is saying that when we call this function, and after the function call, the length of the linked list should be one greater than it was before. And so this will force us to add some extra element. So now if we run the tool on this function, we get back here a recursive implementation. So it will match the self. In the cons case, it just keeps going. And in the nil case, it creates a new node and writes that in instead of the nil. But this isn't exactly the function we wanted. So the function we want is some more efficient function where we just add the element to the head, because here we had to traverse all the way to the tail, all the way to the end of the list and add this new element there. So instead, what we need well, we need a function which will actually just take the self, put it in next, and then add the element right in at the head. But we can notice that in save for us, this isn't possible, because what we would want this function to do, we would want to create this new node where we essentially do like this. We put the element there, and then in the next, well, we'd have to put box as well, but we'd want to do essentially self like this. But here we have a mutable reference of a self, and we want to go to an owned self, which in save for us, you can't really do. But of course, we have some library functions which can help us out. So in the standard library, we have this replace, which I specified here, but you can imagine this just kind of comes with the tool. It knows about the replace and how it works. And the way the replace works is that it takes something and swaps it into the mutable reference and returns the old value that was in the mutable reference. And so now when the tool can use this replace, if we write this slightly stronger specification here, which says that after the function call, the linked list should be a cons, it can't be a nil. So it has to be a cons. And when it's a cons, then the next element after the function call should be equivalent to the linked list just before the function call. So here we're using the star, here we're using the hat. And now when I run the synthesis, well, it can't do the recursive implementation anymore. It's forced to use this library function replace, where it will replace it with a nil, then take this result, construct the new node as we expected, and then at the end write the result back. Okay, so we've seen mutable references. I'll skip the pop, but let's go on to p-class. And here I just want to highlight, it's a bit more of a complicated example. It's okay if you don't understand it immediately, but I want to highlight how the tool can even work with functions where we get in a mutable reference and we have to reborrow to create a mutable reference result. And here in this scenario, the hats mean something slightly different. Well, because here, when we get in the self, right after the function call, the self is going to be blocked because we have to stop using the result to unblock the self. And so here the hat, what it means in kind of simplified terms, what it means is right at the point when the result will expire. So as soon as self kind of could be usable again. And here I'm just omitting the star, but this is the self before the function call. And again, here this hat result is at the end of the result. So not after the function returns, that would be star result, but the hat result means after we're done with the result. So the client might call this function, they might do things with the result, and then this is the value right at the end before they stop using the result. And so this function, we want it to, so the implementation we're trying to get is that it traverses the linked list and it goes all the way to the end and then returns a mutable reference to the last empty list. And what that means is that, for example, if we have a client like this, where the client gets in a mutable linked list, they get an own linked list and they want to append the two. Well, they could call this p-class function. So on the mutable reference, they get an R, which points to the end of the list. And then now if they write in this tail to the end of the list, they've appended the two lists. And so what the specification is saying is that after we're done with the result, once self is unblocked, then the length of self will be the length it was before, plus whatever else we wrote in. So we can't reduce the length because this self.length will always be there. We can only increase it by writing into the result. And we haven't said anything about like recursively traversing to the end. We haven't said we actually want the last element. Just with this specification, maybe there's something wrong. It's not substituting it in. Let's see if I try again. Okay, yeah, this time it substitutes it in. And it actually does the correct implementation. So the implementation isn't too complicated, but the reasoning gets a bit more difficult with the reborrowing. So here it's traversing to the end and then returning the pointer to the link to the empty list. Okay, so now we're done with the demo here. So let's go back to the presentation. And so we've seen essentially how the tool works. So we've seen that we get the functional specification, the functional specification, the function signature, maybe some pure functions that we use to talk about the data types. This gets passed into the tool, and the tool translates this to some kind of precondition and postcondition in what we call the synthetic ownership logic, so SOL. And with this precondition and postcondition, we give it to the actual tool with the engine where it's doing the proof search. And here it kind of tries to link up the precondition and the postcondition to make them match by applying some rules. And once it's done this, then all of those rules will correspond to some program statements. So it will get some output program, and it will clean this up a bit and return that to the user. If we zoom in a bit on this middle part, the actual synthesis, well, here, what the synthesis is doing, well, it's just a proof search. So it's some kind of tree where at each node it has this precondition and postcondition, and then it can apply some fixed set of rules that it has, and each rule will somehow update the precondition or the postcondition. So for example, we have some unreachable rule which just solves it, so it could stop at this point, or we have a construct rule which constructs something, say constructs the result, and here we can see we've updated the postcondition, and it's essentially just building up this tree and searching through it. So part of this tool, kind of the main contributions are these rules specifically targeted at Rust, and the representation of precondition and postcondition, whereas the search, actually going through and expanding the nodes, we've kind of been taken some inspiration from an existing tool for C. So this tool is called Suslik. But the main interesting part are these rules and the representation of the state. So let's actually take a look at that and take a look at how the proof search works. So we'll start with the first function we saw. We'll start with this singleton, and there we'll see how the tool works with owned objects on just this kind of simple example with no specification. So I've put up again this function that we saw, where we have the linked list definition. It's the same as in the demo, and the singleton signature is also the same. And so from the signature, the tool gets this precondition and postcondition. So here, as the precondition, it has some element of type T, and in the postcondition, it has to return a result of type list. And here I've omitted the generics just to kind of keep the thing simple. And in between, it has to fill in some lines of code which will match the two up. And so what the tool sees when it's actually doing a search is just this precondition and postcondition. And I've represented it here as this node in the search tree. And so at this point, it will apply some rule. For example, I have this rule, which the construct rule, and I've monomorphized it to the list here. So we have a rule where we can find a list in the postcondition, and we'll say we construct the list. So here we're doing the nil version. So this is in one direction. Of course, we also have the cons version, but let's explore this nil path first. And so if we apply this rule, well, in the postcondition now we don't have anything because we just constructed the list from nothing. And if we continue, well, we've solved for the postcondition, we just have something in the precondition, and we can get rid of that with the drop rule here. And this just gets rid of it because we're not using it anymore. And in reality, Rust will actually do that for us, so we don't need to include the explicit call to drop. But here I'm just including it to show how the rule has been applied. And now that we have matched them up, you can see they're both just empty. Well, this is one solution. So this could be returned to the user, because we would pretty print it a bit, but we could return this to the user. But of course, we don't really like dropping so much. So here I have it in red because we try and avoid it. So we can backtrack and actually take a look at the cons case. So I've jumped back, and now here we have this construct rule for the cons, where if we apply it, kind of match the right-hand side here with the post condition, then we can replace the list with a T in a box. So if I apply the rule, then you can see we've gotten rid of the list, but now we need to find some T and some box here. And again, if we continue, we have no other choice, since this element T and element T in the post condition, they're generic T's. We can't really do anything with them. We can't construct generic T's. The only thing we can work with is this next box. And the rule we have for it, well, here box isn't actually a struct, but I've special cased it, and we pretend that we can just construct it with this box new. And we just treat it the same way we treat this linked list. And here again, we're matching in the post condition or replacing it with the list in the precondition. So if we apply this rule, now we have the list again. And next, we get the choice again with the nil and the cons. Now, if we choose the nil, then we get rid of the list in the post condition, and now these two match up. So we can say that this element is this element, and this is again another solution. And this is actually the solution that we get. But as I kind of said in the demo already, we can see that if we continued the search, because we have this cons alternative, then if we were to get to this node, well, now we would need two elements in the post condition. We only have one in the precondition. So this wouldn't be solvable, and you could continue, but it would not be able to find another solution. So here we actually have both of the possible solutions in the search tree. And the nice thing about this example is that we've only had kind of two rules. So we've had this construct rule and the drop rule. And of course, the tool, it has many more rules at its disposal. But since we're only working with own things, we were quite restricted with the generics. It only ever could apply these two rules. So the search tree, it remains very small, and it's able to find a solution very quickly. Let's move on to some more complicated examples though. So here we had the specifications where we were talking about getting the head of the linked list. And now let's take a look at actually inside of the tool, how the tool talks about values of objects. So here now I've extended, we still have that I've actually slightly changed the example. Instead of having an immutable reference to self, I've just made it owned. So we don't have to deal with extra stuff of references yet, but the example kind of stays the same. And so we have this owned list, which is called self, and I've added in the brackets this extra s. So the s is kind of the value, the current value of self, and it mathematically represents all of the values that are inside of the linked list. So here I give you some example of the value s. So for example, s could be this kind of construct, which for one, it tells you what the discriminant of the current list is. So here it's saying that the self is a cons, and we've monomorphized it to I32. So if we have the element, then let's say we know that the value is 4, but also we can have other values inside of it. So here the next thing is some value n, and then we can also translate this pure function that we had, this length function, into this the value. And here we know that since the discriminant is cons, we know that the length will be 1 plus the length of the next element, so this n. And now we can also translate the functional specification. So here we just have a requires, no ensures. So the post condition here we have true. And in the precondition, we know that the length of this s value is greater than 0. I'll now zoom in on the search. I'll also slightly simplify. Whenever we have true, I'll kind of omit the pure part here, the facts that we know. And this R is also not important, so I'll just remove that. But we keep the S value. And now we take a look at what we can do. Well, here we can't work in the post condition. We can't construct this result T. So we have to work with the list in the precondition. And one rule we can apply is to deconstruct it. So what it's doing is it's matching on the list and it's seeing which actually discriminant we get. So we get this match by applying the rule. And now this rule actually has two things above it that we have to solve. And what that means is that we have to kind of solve two sub-problems now. We have to solve for the nil case and we have to solve for the cons case. And only like valid solutions for both will result in a valid solution for the whole program. And first, let's take a look at the nil case. So here, what we keep the fact that the length of the list is greater than 0, but we also find out that the value of the list is, well, that it's the discriminant is nil and the length is 0. And you might notice that, of course, this leads to a contradiction because we're saying that the length is greater than 0, but also that it's actually 0. And so we can use an SMT solver and check whether this can imply false. And here in this case, it can, which allows us to apply this unreachable rule. And so the unreachable rule, just at this point, whenever we have false, we can just say we're done. And so this is one solution. And on the other side, it's not as interesting. I've got the full values, but we don't really care about them here. We just have the element T and we want the result T. So we just drop the box as we've seen before. Of course, we could also try and deconstruct the box and see what's inside, but we don't need to do that in this case. So we just drop the box. Here, there's a little rename rule to just get the names correct. But essentially, this is just a simple case where we're done super quickly. And so here's the solution for the cons case, but the one that was actually interesting here was the nil case with the specification. And let's move on to one last example. So this is the example with the push, where we actually have mutable references. And we also have some specification about mutable references. So we'll kind of see what rules the tool has to work with these references and how it views specifications about mutable references. Here, I just want to point out that now that we have kind of the own things that we had before, but we also have references, I distinguish between them with this arrow here or the colon. So what this means is that self is a mutable reference to the linked list here. And secondly, now when we want to talk about the values of these objects, well, we've seen how we talk about values of own things. So we just have this one value which says exactly what the element is. But we also have, for mutable references, we also have this current value. So that's the same as for own things, kind of. But we also have this or the final value, which tells us it will always have a hat. So I'll always represent final values with a hat. And it tells us the value itself will have when it expires or when we say that we won't use it anymore. And so mutable references here, they contain both the current and the final value. That's why we have the pair. And now that we see how the mutable references are represented, we can go on to translating the functional spec. So the functional spec that we had in this example, I've very slightly rewritten it, but it's that in after the function call, so this hat of self, well, it can't be a nil, it has to be a cons, and the next, it has to be equivalent to the current before the function call, the current value of self. And so I've directly translated this kind of with a ternary operator. So we're saying after the function call, the discriminant, if it's cons, then this thing, otherwise this thing. So here we have false. And in the cons case, we're saying that the next of after the function call has to be equivalent to before the function call. I can slightly rewrite this since it has to be cons, otherwise it's false. So I can just say the discriminant has to be cons and x has to be s. And now we have the precondition and postcondition. We don't really care about the Rust spec anymore, so we can just get rid of that, and we can zoom in on the search again. So here we start with this precondition and this postcondition. The postcondition here is empty, so if we didn't have any insurers, the tool could just drop all of the arguments and say it's done. But since we have a postcondition, we actually have to do some work. And one thing we can do here in this case, when we're working with mutable references, well, what the tool does, it sees that in the postcondition, we don't have any mutable reference to self, but in the precondition, we do. So at some point, we must have said, we're just going to drop this variable self, and we're not going to use it anymore. And if I introduce this new name C, that's just a new value, but it's equivalent to what we had before, just so it matches up with the rule here, then we can work backwards and get that this new C value, it has to be cons and the next has to be S. And here we can see that the current value of self, and in the postcondition, the current value has to be this thing that we said we would ensure. And so since the self, it's a mutable reference, and in Rust, we can't have any aliases or anything like this, or just any kind of copies of the self. When we drop the self, when we're saying we're never going to use self anymore in the future, we find out that the current value, it is actually this final value that we were talking about. And so essentially what this rule is saying is that self, it has to end with this C value where it's a cons and the next value is the S, the old value. I'll actually just substitute, since we have C equals this thing, I'll substitute it in, simplify things a bit, and I'll get rid of now this true. In the tool, we would just keep everything on the left-hand side, but here for visibility, I simplified it a bit. And now we can work with this postcondition. So in the postcondition, here we have this mutable self, which we're saying it should have some shape. It should be a cons, but we can't construct mutable references because, of course, it's a mutable reference. I mean, it makes sense, we can't construct it. So in order to be able to create this cons with the value that we expect, we have to apply a write rule. Of course, there are some other rules that we could apply. We could drop things in the precondition, so on, but here we can choose to do the write rule. And that matches this mutable reference in the postcondition, and it keeps the mutable reference. It had some value before it got written to, but we don't care about this value. And it kind of pulls out this value into an own thing. But you can kind of think about it both forwards and backwards. And in this backward sense, we're kind of taking this value and pulling it out into an own thing. And now that we have this owned new list that we want to have some value, well, this is quite easy. We already know how to work with such a list. We just apply the constructors. So I'll apply two rules quickly here. It's constructing a cons and then constructing a box. Of course, we could construct a nil list and then find out that we don't satisfy the specification. So this proof search tree, it would actually branch off and there would be extra work that we would have to search, but I'm selecting here for the correct solution. And I'm just pulling through this, this value. So here, since we constructed the cons, we actually have the correct discriminant. And the next value, it should be S. So here the tail, we're saying that it needs to be S. And so now we're kind of stuck at this dilemma. So here we kind of would want to dereference the self to get the current value out and create this tail. But of course, Rust isn't going to let us take a mutable reference and turn it into an owned linked list. So we need to use this standard library, which is encapsulating unsafe code to pull out this current value S into an owned tail. But we have this function which we've specified, and it's exactly what we need. So it's taking some mutable reference. We have to put in some dummy list that it will substitute in. And as a result, we get out the current value. So here you can see in the specification, we're getting in some mutable reference with some current value, and the result will have that value. The tool will then, it can decide to call this function. And here, when it's calling the function, it will need to construct the arguments. I'll kind of slightly skip over this. So it will reborrow for the self. It will choose to put a nil. It could also, of course, choose to put a cons there. And then it will do the call and use the specification of this function to get the state after the function call. And the state, well, we've put in the nil, so it knows that it's replaced in this nil. And for the result, we've just called the result tail, so it gets the tail here. And now the things nicely match up. So here the tool is done, and it can return this as a solution. Of course, here I've just kind of gone through the rules that you need to apply to actually get to the solution. It would need to do some search and probably some backtracking in all of these alternative branches before it finds the correct solution here. So there we're done with these examples that I've covered. And of course, the tool, it can apply all of the rules that I've shown at any point. It's just some of the rules are restricted. For example, they only work with mutable references. And so it's not going to be able to apply those when we're only working with own things. And here I have a summary of essentially some of the things we've covered, some of the things I slightly glossed over, where the tool, it can work with own things, references, reborrowing functions that kind of return a mutable reference. We can see that we've been working with generic types, which have helped us quite a lot in the examples, because we can't construct generics, so it prunes the tree quite a bit. It can support the functional specifications that you've seen, and it can also create auxiliary functions and recursive calls. But this is kind of, again, inspired by the SUSLIC tool for C, which could also do this. So we just take that idea from them, where it's able to kind of look back in the proof search tree and use some state from before in order to kind of do a recursive call from that. You can take a look at the SUSLIC work for a full explanation. And here currently, what the tool doesn't support, well, I have the list here. So trait bounds, that's kind of more of an engineering thing. I think that wouldn't be so hard to support. For closures, I also think it's not super difficult to extend the tool with closures, because essentially you just have some smaller subtask that you solve for the closure. You get the function signature for the closure, and then you can solve with the full function which uses these closures. For arrays and vectors, it might be a bit more difficult, because usually the way people specify properties about these is by using quantifiers, and the quantifiers, they're not super good at guiding synthesis. So if I have a quantifier, it's not really telling me how I should go about implementing the code to solve for the quantifier. So it could be possible, but it might be a bit more difficult. And lastly, the tool isn't synthesizing any unsafe code. So here that's quite an advantage, because it's actually limiting the proof search, but maybe in some limited cases, we could extend it to actually be able to dip in and add a unsafe code and be a bit dangerous. But right now, I'm not really sure it's that necessary anyway, since the standard library also provides a lot of useful stuff that's wrapped around unsafe code, so we can avoid using it. And so let's get on to some kind of summary of the tool. Well, what we've seen is that by synthesizing for safe Rust, we've been able to do quite a lot, and we've actually been able to do quite a big search because of how limiting the kind of type system is and how limiting generics are. And so with the rules that we've designed for safe Rust, it actually can do quite a lot. So when I was testing the tool, I tested it on the top 100 crates, where we just took signatures from the crates and without any specification, of course, but it would synthesize maybe 1, 2, 3 lines of code. And for those, we would substitute the synthesize function in, and we saw, just as kind of a sanity check, that when we run the compiler on the substituted in implementations, it does always actually type check. Then we took some benchmarks from the C tool for synthesis, and we could see that we would have to write smaller specifications for Rust because we can infer a lot from the signature, and we even get better performance because of this pruning. And then we also ran the tool on some stuff from the internet, so some tutorials, some Stack Overflow examples, and also some test cases from the verifiers, so from Prousty, RusSOL, and so on. And whenever we had these, we would have some specification for those functions. And if we run the verification tool, we did see that it always verified correctly. So it confirms that kind of the synthesized code is correct by construction. And well, I've kind of showed some smaller examples, but the tool can actually do much bigger examples just because of this Rust. So here's some example where it's flattening a tree into a list. So this is actually a rows tree, and it's flattening it into a linked list. And it can come up with, so this whole implementation, so you just have this, you had this function signature, you don't actually need to look at it too much, but it comes up with all of the code here. And for the code, it needed to go through kind of a depth of 40 rules, and the search tree, it got up to 3,000 nodes, but it's able to do this pretty quickly. And so the key idea here is that Rust is able to help us kind of prune the search tree and get us to pretty large programs at some reasonable amount of time. And so I just have a summary slide of everything that we've seen so far. And yeah, I just wanted to highlight that this is the first tool for Rust for deductive synthesis. Of course, there are some other tools which aren't doing this approach of doing the proof search, but this is the first one that's doing deductive synthesis. And the key idea there is that you get code that will be correct for the first time around. And yeah, thank you for listening. And now if anyone has any questions.
If you have any questions, just turn on your camera or use the little wave emoji. But first, I wanted to thank Jonàš because this was an excellent talk, a very, very interesting work.
Thank you.
Hey, Jonàš, thank you very much. I really appreciate it. Looks like a great tool. Quick question is, are the rules written externally or or are they baked into a program?
So the rules kind of in the implementation of the tool, you mean? Or like
yeah, for the tool, yeah, the rules that are in it.
I guess you're asking if you can come up with some extra rules and just add them to the tool. So right now, so the implementation, it's very much a prototype. So I wouldn't really recommend kind of going through and using it so much. And so the rules are baked into the tool right now. But I have a student which is kind of extending the work to actually, because so one downside is that we took this proof search where it's deciding which rules to apply and where to go. It's based on some kind of heuristic from the C tool. And this way to doing the search, I don't think it's the best way to do it. So I think the search could actually get a lot faster if one did it in a slightly different, slightly better way. And so I have a student which is working on essentially re-implementing the tool doing it all in Rust and redoing the search. And there it should ideally be some usable tool that maybe you can even put in the ID and it will do auto completion for you. And I think in a few months this should be ready. And I think there, yeah, I would ideally have kind of pluggable rules where I just can draw from some list of rules and apply those in whichever way. Maybe you add some extra information on how they should be applied.
Awesome, thank you.
Yeah.
There's a question from Pointer Bender as well, who asks, does it use Prusty for verification in the same compilation as the synthesizing?
So I mean, right now, kind of the idea is a bit inspired by separation logic and Prusty, but it's not linked to Prusty at all. So I mean, you can even see that the specification that I write there with the futures and the hat for mutable references, it's more in the style of Crusoe. So like if you take the specification and the synthesized code, it's a bit even more natural to just plug into Crusoe and get the verification there. But yeah, it's not linked, like it's not automatically running any verifier afterwards, although it wouldn't be super hard to plug up, but yeah, it's just a standalone tool. No, so it's not using Crusoe. It's kind of using the same idea as Crusoe with the hat and the future, but this, I mean, it's not using Crusoe behind the scenes at all. You could use Crusoe afterwards to verify the implementation that it's synthesized, but yeah, the tool is separate. Then I guess Pointer Bender has a follow-up question. So which verification backend is behind it? So it's not it's kind of inspired by a verification tool because it's doing this proof search and it's finding some proof for the implementation, but there isn't one verification backend behind it. It's kind of, we had to design our own kind of logic for reasoning about Rust, which is called this synthetic ownership logic, this SOL. And the reason for this is that generally verification tools, say Crusoe and Prusty, they will verify Rust programs that have passed the type checker and the borrow checker, but sometimes they're a bit more lenient. So in some cases, they would, if you had a program that would pass the borrow checker, or it wouldn't pass the borrow checker, but somehow you still got the MIR and you translate it into these verification tools, then since they have some extra information or they trust the borrow checker, then they would say all good and verify the tool. But for synthesis, you kind of need to under approximate a bit. So you need some slightly stricter logic, which is kind of restricting programs that you can synthesize to a set which will always be accepted by the Rust compiler. So it's using its own, it's inspired by the verification tools, but it's using its own logic to reason about the programs. Yeah.
Go ahead, Nico.
Yeah, I have a question. In the example for the push function, you use a rule for dropping references.
Yes.
So Rust has this rule that, like, the lifetime of a reference that is an input for a function, like, expands the entire lifetime of the function.
Yeah.
Like, does the rule take that into account? Like, can you only call the drop ref like at the end of the function? And if not, that could end up like resulting in code that doesn't actually compile if you like apply it or something.
Yeah, so I didn't make that clear, but this drop ref, it's kind of similar to the drop rule for own things that I showed, where it won't actually show up in the synthesized program. It just kind of leaves Rust to do this. And the key idea to understand is that this drop ref, it's distinct from ending the lifetime of the reference. So it's not saying that this reference that I got in, the lifetime ends now. It's just saying I won't touch self anymore. So maybe the lifetime kind of continues in the Rust sense that things are still blocked, I can't use it. But the self, it doesn't exist anymore in this state representation that I have, so I can't write to it, I can't do anything with it. And so because I know there is no other copy of self, then I know not like the data won't change anymore. So even though the lifetime continues and like the future value that I talk about, we're talking about at the end of the lifetime, we know that the current value must be equal to the future value because nothing can change the current value anymore. And so that's, yeah, it's just saying, give up this self alias name for the reference and don't use it anymore.
So, but if you're reborrowing from the reference, then you shouldn't be able to apply the rule?
Yeah, I can still apply the rule even if the reference is blocked. So if I, for example, when we had the function which was returning the tail of the list as the reference, then you would have a drop self within the function, because I mean, that's what you kind of get as a, from the signature, right? You get in some arguments and you return some result, but all of the arguments themselves will be dropped by the end of the function. And you're not dropping the value inside of the reference, you're just dropping the name, the self. Like by the end of the function, when I have a Rust function, all of the arguments will kind of be dropped by the end of the function. But dropping a reference means something slightly different to dropping an own thing.
Okay.
Yeah, so yeah, you're allowed to drop even when it's been reborrowed. Yeah.
I've got a question around the generation or the code generation where multiple solutions are available. Like you mentioned one example where you do some prioritization for not using not going to using solutions where they use the drop. Are there any other kind of heuristics or things like that you use to make sure you're using selecting a sensible solution?
Yeah, so the heuristic, I mean, I didn't focus so much on it in the talk because it's not like been designed specifically for Rust, so I don't think it's ideal in the state that it is right now. But yeah, one heuristic is that it tries to avoid the drop, and the other main kind of heuristic that it applies, it's applying some cost to each node, and the cost is kind of based on the size of the precondition, the postcondition in that node. So if it takes a linked list and it's just always deconstructing, doing lots of matches, then in the sum, when it's always a link, then it will just have loads of elements in the precondition because it's just deconstructed it and gotten all of those elements. And having all of those elements will kind of increase the cost, and so it will avoid exploring that branch of the search space. So generally, it tries to kind of come up with the simplest solution where you don't deconstruct, you don't match as much because matching will give you lots of fields and lots of extra stuff in there. But there is no kind of formal guarantee that it will give you the simplest or the shortest solution right now. But I think that could be improved. I think you could have some reasoning about, say, runtime or something like this, where you say that the solution should be in linear time, and it will restrict the search tree to only programs that are actually in linear time. But right now, the heuristic is just a bit hand-wavy, and it tries to find a simple solution, but there's no guarantee.
I had another question if you still have a couple minutes. I was wondering, why did you choose to use a sort of prophecy style approach for mutable borrows rather than pledges like in Prousty?
Yeah, so the main reason was that it was kind of a bit simpler to design the logic than using the full kind of heavyweight separation logic, I think. And since we decided, okay, safe Rust is actually going to help us and it's going to restrict the search space, then since we're in the safe Rust representation, we can kind of use this prophecy reasoning to do things. But yeah, I don't think there is like a fundamental reason to choose one or the other. It was just kind of out of practical reasons. And I think having a separation logic view of the heap, it would help you, for example, if you're trying to synthesize unsafe code or something like this.
Yeah.
But yeah.
Okay. And if nobody else has any other questions, I have a few very short follow-ups. I was wondering, could you flip the usage of RusSOL around a bit to, for example, help in verification? Like, could you get RusSOL to infer a loop invariant for you, you know, or, you know, rather than for the program infer parts of a specification? Or could you get RusSOL to infer false programs in some sense, you know, like tell you, like, if you're trying to work on a proof of some bit of code, you have your specification, you have you know, a fragment of your function or something like that, and have RusSOL try to, you know, generate counter examples that explains you know, what's going wrong.
I think the counter examples you could definitely do. So, I mean, you just have this representation of the precondition, postcondition, state, and you try and get to some, I guess, state where you have false or something. So that, yeah, I think that should definitely be possible. Inferring specs, yeah, that might be a bit more difficult. I mean, maybe for straight line code, if you could somehow, yeah, I don't think it would be any better than like verification tools, because I mean, a verification tool, I think, is essentially, it just understands each line of code, and that kind of tells it what rule to apply.
Yeah.
Then if you're trying to infer something, you already have the code there. So I don't think this kind of synthesis logic would help you anymore.
Okay. Yeah.